Welcome to Best of CCR session. Now, we are going to have two cool papers picked by the editors from the Best of CCR. So the first one is Professor Precisti from University of Pisa. He's going to talk about an API library for fast packet I/O.
Okay, so thank you, Gianni, for the introduction. And first of all, thanks to the editors of CCR for selecting our paper for this session. We are very honored at that and really appreciate a lot, even on behalf of my colleagues and co-authors. So I want to start with the fact that soft data planes have recently become a very popular way to implement network function. And we have a lot of paper published in literature about in this topic. I just grabbed a few screenshots of some of them, but not obviously, there are many more, obviously, in the literature. However, soft data plane need to run fast to be effective. And to do that, they generally use accelerated I/O network API, like DPDK, Netmap, PFRing, and so on. All of them, obviously, comes with their own grammar, so their own API. So basically, if you write a code, if you write an application, it's supposed to work, for example, with Netmap, but you cannot move it quite easily on top of some other framework. This brings a sort of a portability issue that we believe can be a relevant issue to address, because first, we never know where an application will end up running, and second, we have the evidence of that, because last year, if you think of OpenVSwitch, for example, there are already several incarnations of ES, but then last year in SIGCOMM', there was published a paper about another incarnation of OVS for the one for AF XDP. So we think that also the community think that this problem of portability is kind of relevant. So motivated by that, we thought that could have been a good idea to thinking about a layer which we call Nethuns, that in a sense unify the way the application interact with the network. So we at the moment we implemented, we deployed, we developed and implemented Nethuns, which is going to be the core of this talk, of course. Nethuns is open source and is available at the site that is written on the bottom of the slide. At the moment, Nethuns runs on top of AF, XDP, and Netmap as accelerated frameworks. And for compatibility, it also runs on top of the standard Linux AF packet and the classical pickup. In a nutshell, what is Nethuns? Basically, it's a user space library written in C and supporting multi-queue network cards. In terms of the user, the programmer, what should the programmer do? Basically, when you write an application on top of Nethuns, it simply asks first to, of course, download the library and compile it against the framework that it wants. Can have multiple frameworks. Then just open VS Code or VI and include the Nethuns header and start writing the code by using the API provided by Nethuns. That is it. If you want to move the application on top of another framework, what you need to do is just recompile and you compile the application, and to compile the application, of course, I mean, there is an easy way that is using the CMake. As you can see here, you can basically set one of the framework from a multi-option menu. This is a screenshot, by the way, that I've taken over a MacBook, so I could possibly write an application over a MacBook and then upload it on a Linux server running AFXDP, and the things go straight. So what Nethuns actually provide? Nethuns provides two kinds of abstractions. One is the socket abstraction, although you have to be, I want to be straight. Nethuns is not a socket. We can't call it a virtual socket, but I mean, it's not a real socket. But anyway, it has the semantic of a socket. So you're going to have the open call, you can have close, the bind, and so on. So the socket abstraction is the point of access to the wire, basically. And also it has a ring abstraction, which is the point of access to the packet data, so packet descriptor. The rings, normally you have one ring for direction, for Rx and TX within the socket. And the fact that we have rings, this enables zero copy passing of packets of data, I mean, across multiple workers. Whenever the underlying socket provides rings, we use the rings that we have. Otherwise, in case, for example, the pickup does not provide rings, the framework itself builds a ring at the cost, of course, of copying the packet within the ring. But this is, I mean, when you use the pickup, you don't have probably performance in mind, so you can just pay that without any particular problem. The framework, I mean, the library itself manages the memory for allocating rings and buffers for packets, so you don't have to do anything, you don't have to worry about that, just it's the library that do it for you. In terms of API, the API that is provided by Nethuns is pretty much the one you can expect from a library like that. So you have a basic number of calls, which is the opening the socket, binding to a device, which is an interface and an hardware queue. You are receiving, releasing the memory, and so on. In addition, there are more specific API, which I didn't list here because, I mean, I don't want this talk to be a man page. And finally, the framework itself offers an optimized, cache-friendly, single producer, single consumer queue, it's very optimized to run very fast and to allow dispatching packets to possible multiple threads and multiple workers. Now, this is the way I solve the interface. Now we need to see if it's effective in practice or not. So to do that, we need to assess and evaluate the amount of overhead that it can introduce with respect to native frameworks. To do that, we simply set up a simple test bed in which we have a sender and receiver, and we are running application that both send and receive packets. Both the application running the native socket and both in the Nethunized, I would say, application that runs on top of Nethuns, which it runs itself on top of the socket. Of course, we are doing this evaluation only for the AFXDP and Netmap because they are the two frameworks that run fast. It doesn't make any sense to do it for the other two sockets. So basically, we are running when we test Nethuns, we are running Nethuns Send and Nethuns Meter, which has two applications that ships with the library. While when testing Netmap vanilla, I would say vanilla, plain Netmap, we use PackageGen, which is the flagship application that ships with Netmap, and XDP SOC, which is the one that ships with AFXDP. Okay, so are testing both direction, sending and receiving. So let's start with the sending. So when I transmit packets, what we do is we try to send as many packets as possible over 40 gigabit links between the two servers. The two servers have 8 cores, and of course they have Intel 40 gigabit interfaces, multi-queue interfaces. So we run packet-gen and XDP sock for native for plain Netmap and FXDP plus Nethuns send, and we see the result. So the important thing is we don't want to, we would like not to see any overhead, or at least to keep the overhead as small as possible. So the comparison here must be done between the red and the purple, and between the black and the blue, because the red and the black basically add Nethuns to the plain underlying socket framework. So what we have here is, by increasing the number of queues, we can see that basically the overhead that is introduced by Nethuns is really negligible in the first two cases, when we have 1 and 2 hardware queues, which means 1 and 2 threads. Then after that, basically, we don't see any difference. And even the difference that we see now is really, really negligible. I think we can stand with that, I think. For the receiving part, more or less the same reasoning applies. As you can see, first a comment. We have a theoretical line rate which is around 60 million packets per second, because we use a minimally sized packet. We can't get close in any case with our hardware and with the framework that we have. But this is, almost it's reported in the literature, nothing new. In the receiving part, so we are sending as many packets as possible. In this case, we are reaching about 42 million packets per second, which is this number here. And we are receiving over an increasing number of hardware queues. And again, we see that once beyond 2 hardware queues, we don't see any difference. Even when we use 1 queue, we see that we have an intuitive result, which is from the black and the blue. So we have a little overhead introduced by Nethuns over Netmap, which is pretty reasonable, because Netmap is very, very optimized for receiving, while we have a kind of a counterintuitive behavior here, because it looks like Nethuns increased a bit performance over FXDP, which is not really reasonable, because the underlying engine is exactly FXDP. Probably this is due to some implementing issue. There might be some fortunate placing of the descriptor in memory, some good cache-friendly effect that we see here. But the result is so small that it's not even worth to comment it probably. So once we have these results, we decide, okay, this is just too dry. We want and we need to test Nethuns in a more practical use case. And so we decide which application can we run on top of Nethuns, and we decided to use OVS, Open vSwitch. There are already, the thing is, the user space data path of OVS uses a generic NetDev interface, which is called NetDev. There are already 2 implementations of the NetDev, which is DPDK and AFXDP. We added our own, so basically we implemented a NetDev version of Nethuns, a Nethuns version of NetDev. The implementation, by the way, wasn't that much, because the details are all buried in the library, so we didn't really have to spend so much time, and especially me, because I wasn't the one that did it, so I can easily say so. But it was like a few hundred lines of code change, and after that, we also have now OVS over Nethuns, which brings for free Nethuns, OVS over Netmap. So it is kind of interesting to see what happened with OVS over Netmap as well. Again, need to test it, need to see what happened. And the comparison here is between the red and the purple box, which compare OVS over plain over AF XCP, so the paper of SIGCOMM' last year, and OVS over Nethuns over AF XCP, which ideally they should have the same performance, but intuitively we might expect a little degradation of the red one. Instead, it looks like it's having a little better performance. Again, this is not really intuitive, but most likely it is due again to a cache-friendly placement of packet. I mean, it depends on implementation in the library, because there is no other reason, honestly. What we can see is that performance saturating in any case when we read 5 or 6 hardware queues. And the final thing which is interesting and which wasn't known is that Netmap, which is the black box here, looks scaled like almost linearly. Unfortunately, we ended up with the cores. We didn't have any more cores because we isolated 6 cores out of the 8. We reserved 1 core for interrupt and 1 other for other processes. Maybe if we went to 7, 8, and so on, probably we may have a linear behavior at least up to some point of Netmap. By the way, in this case, we didn't send 42 megabits per second because it was enough to send half. We sent 21 megapacket per second, so just one instance of Netmap from the sender, because it was enough. We didn't have so much power at the receiving side. So then we have in the paper we report another possible use case, which was a traffic generator. We actually needed to have a traffic generator, a replayer of pickup traces. We didn't have it over Nethuns, so we had to change between building our own from scratch or reusing some other, and we did for the second. We went for the second. We took a Netmap replay, which comes from Netmap. We changed a little bit, and we got it with same performance as the original one. So basically, this is the summary. What we've done is we presented Nethuns, a user space library that should provide socket-independent abstraction for network programming. Currently we support Netmap in FXCP for accelerated framework and the standard AF packet and lead pickup for compliancy. This makes it easy to port application over different framework. We haven't seen performance degradation in simple dry test and not even in a more compelling test like the one with the OpenB switch. Once again, Nethuns is open source, so help yourself. We are very glad if you go to the site and download the code. There you can find example, how to use documentation, and so on. That's it, so thank you very much.
Any question?
So one of the hard parts for these type of unifying libraries is usually not the 90%, but the 10%. Namely, if you have an existing application that uses some library, it uses some specialty socket control, some IO control function that you haven't implemented in whatever it is. Did you find this, or are all the libraries that you sit on top of sufficiently similar that there isn't that corner case that would basically require in-depth understanding of what did the author of this real application really try to do here, and how do I implement this in Nethuns?
Well, what we have, if I understand well, what there is already out there, the thing which is similar can be the lead pickup that used to be the one that unified But unfortunately, the leap pickup have some drawbacks. And in particular, they do not allow they don't give you a ring. And so they give you, what they give you, you're never guaranteed. Once you read a packet and you go to the next one, you are never guaranteed that the first packet is still there. So you cannot spread it around different workers. That was the motivation, because otherwise, that's a good point. For example, leap pickup exists for Netmap, so we wouldn't need to do that. Instead, with this, we have this other feature.
Any other question? I do see, oh.
I don't know if this is a sensible question. What about DPDK?
I expected this question. Yeah. Okay, so there are several ways I can respond to this question. So the first thing is, with the one that we chose, basically we kind of cover the spectrum of possible platform. But this would be too easy. Then the thing is that, as in our understanding, the PDK is built on a programming model which is way far from here, from the one that we use. So basically now we are kind of using sockets which have a semantic of a socket, which is not the case of the PDK. So it makes it, obviously it could be good, yeah, but we haven't done, too much. We don't even know if it's worth, I have
another comment about your sort of what you see as an anomaly in your experiments.
Which one, sorry?
There seems to be an anomaly where you say, hey, that when I add Nethuns, I'm getting better throughput. It's actually that, my thought is slower is actually faster. The reason is that you're seeing a lot of loss as you receive. And the fact that you have an interface that slows down what you dump up into a queue ends up actually getting you that slightly better throughput.
Yeah, that could be a good reason. We have started some code analysis, and we found that possibly that could be an idea, but yeah.
Thank you very much, Gregorio. So.
Thank you.